This video is about linear equations in two variables, but we'll start with what we know about linear equations in one variable. An example would be 3x plus 2 equals 14. We know that this is a linear equation. Primarily, we can see that the variable has no exponent on it. With no exponent, technically it is an exponent of 1, and that's what makes it a linear equation. There are some other technical details about a linear equation, but we most often are seeing no exponent on the variable, and this equation only has one variable, x. It would still be a linear equation in one variable if there was a variable on another term, as long as it was the same variable. So it would still be a linear equation in one variable. We have steps to solve a linear equation. What we're doing is undoing the operations that are occurring to the variable. 3 multiplied to the variable, and then add 2. So we do the opposite of those steps and make sure to do it to both sides of the equation. This process is often called isolating the variable. 3 times x, so we'll do divide both sides by 3. And it's called isolating the variable because that's how our solution looks, with the variable all alone on its side of the equation. This equation is called solved for x, and we've isolated the variable. No coefficients other than 1, because x is equal to 1x, but we usually leave that coefficient of 1 off, and no other terms on this side of the equation. X equals 4 is the solution because this is the number that if it was in place of the variable, the equation would be true. 3 times 4 is 12, plus 2 equals 14. Linear equations in one variable most of the time have one solution, that x equals 4 in this case. There are some other equations that might lead us to no solution or all real numbers, but we'll focus more on the equations that lead us to just one solution. 4 is the only number that would fit in this equation and make it true. Any other number would lead to a result that does not equal 14. And we can graph this solution on a number line. So here's a number line, a horizontal line. I've put 0 close to the middle and shown that each increment to the right is equal to 1. So to the right increasing by 1, to the left decreasing by 1 into the negative numbers. And on the number line, we'll find positive 4, our solution, and plot a point right there. So we have a visual representation of our solution with a number line. X equals 4 is shown by plotting this point on 4 on the number line. Now we'll look at a linear equation in two variables, and we want to pay attention to what sort of solution we get and how we have to plot the result when it comes to graphing. And keep in mind that a linear equation with one variable has just one solution, and we graphed it on a number line. Here's our first example of a linear equation in two variables. It has the same visual clue that our variables do not have exponents, and now we see two different variables, x and y. We have seen some equations in two or more variables as formulas, and there were times where we wanted to take an equation and solve for x or solve for y, isolate one of the variables. And that was still about doing the opposite, but we weren't able to get a number for a solution. Like if we wanted to solve for x, we would see that we are adding y to x, so we'll do the opposite, take away y. We're still doing that to both sides of the equation, but we need to know that 5 and negative y are not like terms, so we can't combine those. And we should already have a heads up that we're not trying to get to a numerical solution. An equation or formula with two or more variables, if we don't know the value of some of those variables, we can't get a numerical solution. The best we can do is this type of rearranging of a formula to solve for a variable. We would leave the right side as 5 minus y, and an equivalent way to write that would be x equals negative y plus 5. Keep in mind that they're two terms that are not like, they cannot be combined, so we're keeping them as two separate terms, positive 5 and negative y, and those terms can go in either order. So here's solving for x, but we don't have that numerical solution. So you need to keep in mind what a solution actually means. In the previous example of the equation with one variable, we found that x equals 4. And it was the solution because it was the number that into the equation would make it true. Now with two different variables, a solution would be a number that can go in place of each variable. And not really the same number, but just two different numbers, a number for x and a number for y, that if we put those two numbers in the equation, it would make it true. There are some strategies for how we pick numbers, but really anything works as long as x plus y equals 5. So 1 and 4 would work, or if x was 3, then y would equal 2. 3 plus 2 equals 5. Or if x was 0, y would equal 5, because 0 plus 5 equals 5. What we're doing here is a little bit like solving by inspection, which means we just look at this and some numbers come to us. X plus y equals 5, so let me just think about a pair of numbers that added up would equal 5. Or what we're starting to do with this example is I'm going to choose a number for x, let's say negative 2, so what would y have to be now? So that negative 2 plus y equals 5, negative 2 plus 7 equals 5. Solve by inspection works on some equations, but it's tougher to see in different equations what some solutions might be. So we end up using this strategy a little bit more, where we choose some number for x, or one of the variables, and figure out, well, what would the other variable have to equal to make this equation true? If x equals 8, now we're talking about 8 plus y equals 5. And if we're not seeing readily what y equals, we can solve this equation. We're down to a linear equation in just one variable. So a very common way to handle equations in two variables is to choose a number for one of those variables. And once we put it into the equation, we're looking at an equation with just one variable, and we have all sorts of practice at solving these equations. We're doing the opposite of what's happening to the variable, where you're thinking about isolating the variable, and we would see that y equals negative 3. And maybe you had already come up with that on your own. But we'll use these ideas for equations that are a bit more complex. So here's where we are so far with linear equations in two variables. When it comes to solutions, we're not able to find just a single numerical solution. We have to look at pairs of numbers, a number for x and a number for y that could work. And it leads us to many different solutions, but they are all solutions because it's a pair of numbers, one in place of x and one in place of y, that will make the equation true. The way that we write these pairs of numbers would be with an ordered pair. The two numbers in parentheses separated by a comma. So the first solution we could write as 1, 4. This ordered pair always has the x value first and the y value second. When we're dealing with x's and y's, you can always assume that x goes first and the y goes second. If we're dealing with other variables or some other case, then somewhere you would have listed for you how the ordered pairs should be written, or what they stand for. So x comma y is what we can always assume, unless there's other information about the variables and the ordered pair. So 1, 4 is one of our solutions. 3, 2 was another solution. 0, 5 was another solution. Negative 2, 7. 8, negative 3. So we have a list of 5 solutions, and there are actually an infinite number of solutions that we can find to this equation, because we can choose any number in place of x. I could choose a nasty decimal number to work with, but there would still be another number for y that could be added to this x to equal 5. If x equals negative 12.3874, then y equals 17.3874. Another solution because x plus y equals 5, exactly what's written in this equation. And x could even be an extremely large number, but we would still have a number for y so that x plus y equals 5. In this case, it's negative 10,384,687. Another ordered pair solution because x plus y equals 5. We have two numbers, one in place of x, one in place of y, that make this equation true. Now let's talk about how we would plot these ordered pair solutions. The linear equation in one variable had the solution plotted on a number line, a single horizontal line. But now our solutions are made up of two numbers, so we use the coordinate plane to plot two numbers. Here's our coordinate plane with the x-axis horizontally, the y-axis vertically, and we're plotting each of these points. The point 1, 4 means x equals 1. It's positive, so we're going right on the x-axis. and y equals 4, so we'll go up 4 and plot a point. Our next point is at 3, 2. Next at 0, 5, so horizontally 0, vertically 5. The next point has x equaling negative 2, y equals positive 7. Next, x equals positive 8, y equals negative 3. And hopefully we can see an explanation for why these are called linear equations. When we plot all the ordered pair solutions, we're able to connect all of those solutions with a straight line. Arrowheads to indicate that this line extends forever. It's how we'd be able to see the solution x equals negative 12.3874, y equals positive 17.3874. Think about x equals negative 12 approximately, y equals positive 17. It would still be on this line, it would just be up above the coordinate plane. If we extended it, we would be able to see the line cross right through that point. Same with our other ordered pair down here, it's just way off the page. And all the points that are on this line that we didn't plot are other solutions to the equation. Like right here, we have a point, and that point corresponds to x equals positive 4, y equals positive 1, and that is another ordered pair solution to the equation. If x equals 4, y equals 1, and 4 plus 1 equals 5. That works with any point on the line that we find. Back here, x is negative 1, 2, 3, 4. Y is positive 9. And negative 4 plus 9 equals 5. So it's another solution to the equation. And if we were careful enough, we could find fractions and decimal numbers that would be solutions also. This is the point x equals 1.5, y equals 3.5. 1.5 plus 3.5 does equal 5, another ordered pair solution. So as long as we know just a couple of ordered pair solutions, we can plot the line and find all sorts of other ordered pair solutions. And that's one reason why graphing is so important when it comes to linear equations in two variables. So to sum things up so far, we have that linear equations in two variables can have an unlimited supply of solutions. And these solutions are ordered pairs, a number for x and a number for y, that when both are in the equation, it makes the equation true. And plotting these ordered pair solutions requires a coordinate plane. And now we see that different ordered pair solutions to an equation all line up on a straight line on the coordinate plane.